All right. Good afternoon, everyone. My name is Robert Scott. I'm the president of Baywork, and also I oversee technical training at Valley Water. Welcome. We're glad that you're joining us today. If you haven't already, please put your job title and your organization into the chat so we'll know who's in the room. And also feel free to put any questions or comments that you want in the chat throughout the presentation. And near the end, we will have a survey. Now I want to introduce to you our presenter for today. His name is Denis Ruttenberg. He's an associate civil engineer at Valley Water. And I'm just going to turn it over to him so he can talk to us about fundamentals of fluvial geomorphology. Go ahead, Denis. It's on you.
Great. Thank you, Robert. And just to check, can everybody, hang on, I'm going to share my screen. Can everybody see my screen?
Yes, we can.
Great. And still presentation
Yes.
mode. Awesome. Yeah, great. Thank you, Robert. Thank you, Baywork, for inviting me to speak. Like Robert said, I work for Valley Water. I have my master's in civil. I've worked in consulting and government for over 20 years doing restoration design. And I have some specialties in fish passage and boulder weirs. But yeah, I'm going to do a quick presentation of Morph. This is actually two different presentations over 2 hours worth. So I compressed it down and try to go quickly, hopefully not too quickly, and work my way through it. Talk about geomorphology, talk about habitat restoration, specifically in this case, fish passage. So kind of opening slide here. This last summer I went to Denali National Park and took a picture of this braided Arctic river. Pretty amazing. If you ever get there, go to Alaska. Pretty amazing. So outline of what I'll talk about here. Basically some geomorphic fundamentals, geomorphology, concepts, what is a bankfull channel, and then go through some stability and channel evolution kind of concepts. And then from there, I'll talk a little bit about fish swimming abilities and fish barriers and how to hopefully solve those and actually enhance a stream. So there's our fish, thinking about geomorphology. So what is fluvial geomorphology? Fluvial geomorphology, just kind of put the words together. It relates to flowing rivers and the shape of the rivers. So according to the University of Massachusetts, it's the study of interactions between the physical shape of a river and their ability to transport water and sediment and the kind of landforms that they create. But the fundamental question, and I keep going back to, is geomorphology is basically about what does a channel want to be? Where does it fit? What does it want to be ultimately? Kind of a Venn diagram here. So fluvial geomorphology, as I mentioned, includes a lot of different aspects. Conceptually, in my mind, at least, it encapsulates geology, hydraulics of a channel, and then the ability to transport sediment. And in the context of an engineer and a planner, these things all are important to the planning, designing, and permitting of a project. Lately, the regulators have a great interest in designing channels to be bankfull and self-sustaining. So it's pretty relevant to permitting and actually pretty relevant to the ecology and the biology of the channel. And then of course there's other factors. So this kind of is a little conceptual chart of that fluvial geomorphology is an integration of so many different fields to study and putting it all together, putting together the puzzle pieces. Where does a fluvial geomorphologist fit in the scheme of things. Yeah. So looking at it from time and space, a geologist will look at like mountain ranges or continents or tectonic uplift. Fluvial geomorphologists will be more on a reach scale or looking at longer reaches of river. An engineer and a planner, they may be more focused on like 100-foot length of stream or stream bank. So, this kind of a little concept of how a fluvial geomorphologist fits into the scheme of things. Real quickly, concept of confined channel. This is relevant to classifying channels, but a confined channel basically is in size and deep cut, partially confined, and you might have a floodplain on one side. And then unconfined, you have like a bankfull channel and then a floodplain on both sides. Bed form. So this is kind of a simplified graphic. There's a lot of nuances of bed forms, but conceptually you have a bed form in a channel that's actually a moving bed form, say a riffle pool. There's perturbations in a bed form, which should be in the form of a nick point, and I'll show you on the next slide what that looks like. But basically, it's like a little notch in the channel that works upstream. And then conversely, and we had a talk on fire this morning, you may have like a sediment pulse that's produced from runoff and sediment from a fire that's working downstream. So in terms of definition, here's a picture of a nick point, but otherwise an abrupt change in the channel bed form. And you can see that, this may or may not be natural, depending on the context, but something happened. Something happened downstream. And you can see the turbid water, this thing is rapidly moving upstream in a very abrupt change. Another definition is dynamic equilibrium. So channels are going to naturally move. They're going to move laterally and vertically, and they'll move in and around a longer term mean. If it's in kind of an envelope of motion, you might be able to call it a dynamic equilibrium. And I'll show more about it here. Hopefully you can read this. I'm sorry it's a little fuzzy, but this graphic shows something from A to E, where at the top you have like a static system, something like a water faucet, no change whatsoever. But working down, if you have maybe one variable changing or more, the graphic here just to go back, the graphic here on the left, it refers to one point in a channel, and then how does the elevation of that point in the channel change over time? So this is not a graphical profile. This is one location in the channel. And basically, if you were to put a monitor there, monitor elevation, what would happen to that one point over time? So static, nothing changes. Steady state, you have maybe kind of minor oscillations. Dynamic equilibrium, there's kind of a downward trending, like say you have subsidence downstream and it's slowly subsiding over time. So you'll have a trend going downward, but then you have lighter oscillations. Metastatic equilibrium is when you might say have a dam break or something blowing out in your stream. Just a very abrupt and severe change. Dynamic metastatic equilibrium is sort of a combination of C and D, where you may have like something like a dam break or a severe subsidence event from a seismic activity, but that may only occur every 20 years. So that in between, for about 20 years, you get minor oscillations, and then you have an episodic event. So Robert, if you could help me monitor chat, and the question for those on the call, what is the most profile, what, excuse me, what profile is most typical of the creeks and rivers in the Bay Area counties? If you were to pick one or more, A, B, C, or D, where would you peg? And
All right,
yeah,
we see some responses coming in. We got B, C. Anyone else? Any other thoughts? A, B, C, D, or E? B and C, I hear.
yeah, well, I think those are all good. There's no one clear answer, but yeah, I tend to think something like C. B
Got
is probably less likely. It could even be E, depending on where you are, you know, like if something happens in your system. Yeah, so great, thank you. I'm gonna keep moving here.
It looked like B was most popular. Some people had B and C, but there are more B's there than any of them, by the way.
Yeah, that's pretty close to
All
what
right.
it is. Yeah, but with climate change and other factors, you know, I'd lean towards C, but it may be a combination of B and C. But good, okay. Plan form. So the plan form of a river, it can take different forms. It could have a single thread, or it can have like a braided thread. If it's a meandering river, there's all kinds, and you don't have to pay attention to all these details here, but a meandering river has a lot of quantification and geomorphology as to how it meanders and how to study it and design it. Namely, it's going to create a meander corridor. And keep in mind, a river is not a static system. Like I mentioned before, the meanders are going to move over time. Like I put this image of a snake here. It's a lot like that. Like the way a snake moves, it creates tension and compression along the length of its body. You know, I'm not a herpetologist, but the notion is that it's a living kind of plan form. It's not static. And there's exchanges of stresses that pass through the system. So those are all quantified. Sinuosity is a good one to know. It's basically the wavelength, the length of the channel over wavelength. If it's more sinuous, it's more windy. If it's less sinuous, it's less windy. For all the scientist nerds, you can actually look at Leopold and Woolman 57. He quantified, or he actually did a bunch of measurements and came up with a relationship between bankfull discharge and slope. And based on those relationships, you can roughly peg what kind of stream you're going to have. Is it going to be braided or meandering? And you can use this chart based on bankfull discharge and slope to figure out where you are. So given bed form and plan form, morphology, there's all kinds of systems of classification. And it's human nature, like we want to classify and deconstruct everything, try to predict it. Roskin has a system where he has a channel from A through G. I think this is commonly used among a lot of people. It's a form-based classification system. So an A channel is conceivably in the headwaters. And then as the letters increase, you get lower in the system, like A, B, C, D. There's other kind of variations of it. Anyway, it's the Roskin system. Another kind of approach and classification is process-based. So here we see SHUM. What's important to note here is, again, we have headwaters, a middle part, and a bottom part, but this is differentiated by characterizing the upper reaches as a zone of erosion and sediment sourcing. And then in the middle part, you have a zone of transport. But then when you get down to the bay and like a braided or a dune ripple channel, it becomes more of a zone of deposition or alluvial fan. So conceptually, you can characterize it like that. Montgomery and Buffington took it further, shown further, and they came up with a system that identifies channels from being a cascade all the way down to a dune ripple. And on the left are kind of like schematics showing what they generally look like. On the right, we see a profile. So like an A channel, a cascade channel is big boulders, kind of headwaters. It's pretty rough, pretty steep. And then the middle part, B, C, and D, step pool, plain bed, pool riffle, they could be generally transport reaches. All the sediment goes through. And then in a dune ripple, you might have a depositional reach, process space. There's a lot more to this, but other processes like where does the woody debris habitat occur, where there's scour, where does sediment transport initiation begin. So I'll keep going. Again, Montgomery and Buffington. So there's a lot to take in here, but what I would just like to show you is let's just look at one variable, stream gradient. So if we start at the downstream end at a dune ripple channel and stream gradient increases, you can see how a dune ripple channel in the middle reach, the same channel would become a pool riffle, plain bed, and step pool and cascade. So just looking at stream gradient here on this chart, you can kind of see where the context of where your channel fits. And Robert, I think you're going to make this available to people to see. I'm happy to share it. I know there's a lot of information here. So,
Yeah, I put the presentation into the chat. Is that what you mean?
Yes.
Yeah.
Okay, great. Okay. Riffle pools, those are important concepts. Okay, we got 16 minutes. Just kind of doing a time check on myself here. Yeah, I'm going to try to go a little faster. A riffle pool. Here's a concept of a riffle pool. Again, a meandering channel. On the outside of the bend, you have a scour hole. The riffle is on the straight part of the channel. And this is pretty common for restoration projects. The typical riffle is 5 to 7 times the bankfull width. And then the slope of the channel is typically from riffle crest to riffle crest. Bankfull channel. Oh, I think we're pretty good. I'm just checking my time. What is a bankfull channel and why does it matter? So maybe these are kind of wordy descriptions of bankfull, but the notion of bankfull, it's the channel where the maximum work takes place, the maximum amount of sediment moves in a channel. It's morphologically significant because most of the sediment is being transported in this bankfull channel. Once it gets beyond that flow, that bankfull channel becomes a floodplain flow. With a bankfull channel, you have a kind of a dynamic equilibrium of depth, width, and flow area. And I'm going to show you some regional curves and relationships on how to identify that. So a graphic of the bankfull channel. Thank you. Again, a lot of the work for a bankfull channel occurs within a certain width. And because of that, you don't really see mature vegetation in the bankfull channel. However, at the edges of a bankfull channel, you'll see something like mature trees, and you'll see bar depositions. It's a working channel and in dynamic equilibrium, as I showed you before. There's a good guideline, the Valley Water Design Guide 19. There's a link right here. So it talks a little more about bankfull channel. There's a lot of good literature on bankfull channel. It's an important concept to know. We'll talk more about it here. So again, for those who like have fun with equations here, where does the bankfull, what is the flow associated with the bankfull channel? Like when the bankfull channel is full, what is that discharge, that flow? It's also sometimes called effective discharge, dominant discharge, or channel forming flow. It's where the maximum sediment transport takes place. So if you look at this graphic, from left to right, you have an increase in flow. I kind of traced it here, not so great. And then there's two other charts. There's the flow frequency. So as the flow increases, it's less frequent. So you have like a flow frequency curve. And then the other curve is the amount of sediment that gets transported at a particular flow. So if you multiply the flow times sediment rating, you're going to end up with a sediment load curve. And where that sediment load curve maxes out is an indicator of the greatest amount of work in your bankfull flow. I don't have my citation here, but a lot of great work was done by Woolman and Miller on this. They have like sort of a milestone paper on bankfull flow. But there you go. Here's a picture of a channel. I took this last year. Actually, I was hoping in this last storm we get a bankfull discharge, but I don't think we did. This is a channel near where I live. So I went out and took a photo during a storm last December. I think it was about bankfull discharge. And I went back about a month later. I took this photo. So bankfull markers, conceivably, you have like a channel here. And the bankfull markers, again, are like mature trees. You might see the top of a point bar, slope breaks, and so on. Right, so bankfull discharge and dimensions. Again, bankfull discharge is somewhat equivalent to a 1 to 1.5 year return flow. If you're in an urban setting, it's probably closer to 1 year because you have a lot of impervious. In a natural setting, it's more like a 1.5 year. You can do field measurements to measure that. And there's also regional curves. So I'll show you regional curve for that. Again, for bankfull dimensions, there are regional curves. And you can also go out in the field, like I showed you this image here. You could actually go out and physically measure these dimensions and try to correlate them to bankfull. You can also determine it by hydraulic modeling. And some of this is also covered in the valley water literature, as well as many other sources. The reason it's important is when you do a restoration design, you want to be able to identify the width of the channel that you just want to leave. Like when you build a bridge, you want to give it a free span of a certain width. So the channel you can naturally adjust cross-section wise and bed form wise. Just give it the room, it will naturally grade and degrade. So a bankfull channel is a concept that will help you do that. Regional curves. This is done in Leopold, one of many. Ann Riley has some great curves for Bay Area. I'm just showing you this one in concept. If you have the watershed area, I don't have the graphic here, but you can determine the regional curve for discharge. But you can also, with watershed area, you can also use the regional curves to the nomograph to kind of plot out what your bankfull depth is. And if you go up the curve here, you can plot out, okay, bankfull width is probably about 4 meters, and bankfull depth is probably about 0.6 meters, and the cross section area is about 4.5 square meters. So you can use these regional curves to help you design a channel. Let's see here. 23. Channel stability. So maybe some of you have seen this. This is a pretty handy tool. It's called Lane's Balance. It allows you to interpret a channel, and it allows you to interpret what happens if something changes in a channel. Channel evolution and stability. So it's basically a graphic that's a manifestation of this equation below, where we say the sediment transport rate times the median particle size is proportional to the product of the flow times the slope. But who wants to look at that? We want to look at that. We want to look at the nice graphic to help us interpret it. So on this next slide, if we take the example of a riffle pool, so what happens, say, if the slope increases on a riffle pool? So if you go over here, you know, in the terms of the balance, if the slope gets steeper, then it's going to tip to the right. If it tips to the right, it's going to indicate that the channel is going to degrade. It's going to erode. And intuitively, sure, you know, the channel gets steeper, shear stress goes up, the forces go up, it's going to scour. But in response, the channel is going to find an equilibrium. The bed material may get coarser to compensate for that. And then the balance may tip back to being balanced. It's going to find a new equilibrium based on how it changed. So you can run through all kinds of different scenarios, but it's, like I said, it's a pretty handy tool that's a manifestation of a lot of scientific knowledge there. Shum, let's see, 26 minutes. I guess I can go through this really quick. This is another evolution model by Shum. If we start with a channel that's degraded and eroding, and you say you have like the slope is increasing, you have a neck point passing through, you're going to see a channel that's going to experience incision. It's going to start down cutting. And then over time, the channel will most likely widen. It'll finish down cutting and stabilize, and then it's going to get wider. And then when it gets to a point where it's too wide and where the sediment transport rate is less than the supply. So if there's so much sediment coming in, but it's not passing through, the transport rate just doesn't compensate for it, you're going to start seeing aggradation. So eventually, according to the Shum model, you get to a point of dynamic equilibrium where, as I mentioned, the bankfull channel is sort of the, you know, what does the channel want to be? It's the channel is going to want to be this bankfull channel that's going to oscillate around depth, with a certain depth, a certain width. If you give the channel room, it will find its way to become a bankfull channel in a natural system. What if you don't have a natural system, which is basically everybody, you know, pretty much every situation? Yeah, you get urbanization. Like I mentioned before, the bankfull flow drops from a 1.5 year to, say, a 1 year flow. If you have a reservoir upstream, it's regulated, it completely changes the bankfull dynamics. Maybe you can adjust the regional curve or try to estimate bankfull, but in a highly regulated system, it makes it complicated. Climate change, you know, we're having, depending on where you are, we could have more frequent and higher winter peak flows, and maybe in a shorter time period. Drier summers, maybe less precip overall, maybe more. Yeah, so these things affect your ability to assess a channel geomorphically. On a side note, tidal channels are a different animal altogether, but there's a lot of relationships that were done by Phil Lands and other folks. I think Jeff Haltner, a lot of locals, local and great scientists. You can apply the same approach to the design of a tidal channel, but instead of using discharge, the driver for that is tidal prism. And there's a lot of equilibrium relationships for dynamically stable channel based on tidal prism. All right, so I have 30 minutes. All right, fish barriers. Hopefully people are familiar with salmon. So again, this is a kind of a complex chart, but my point here is to show the salmon life cycle, that they lay eggs in the streams, the eggs hatch, they become juveniles, they grow up, and they go out to the ocean, and then the adults come back and they spawn in the streams. A common problem is that the adult fish cannot get back to their spawning grounds. They get trapped at barriers, like a dam. The reason they get stuck is the barrier exceeds their performance. So here on this table here, this slide, I show some commonly used hydraulics that help characterize whether or not a fish can go upstream. So for salmonids, they look at the primary things they look at are swim speed, how much a drop is, hydraulic drop, and then the depth of the water. Fish can swim a burst speed or sustained speed. Adults can swim very fast. The jumping capability of an adult is much greater than a juvenile, typically 6 versus 12 inches. If you want to get into more science about it, you can look at kinetic potential, b squared over 2g. If the fish is swimming at a certain velocity, that's how high it can jump. Or there's also relationships to the size of the fish and how high they can jump, fork length. Adults need deeper water. So this is kind of in flux. It's possible that a 12-inch drop is sufficient for juveniles, but that just really has to be site specific. Sometimes people get locked into 1/2 foot, but that's site specific or project specific. Here's a graphic showing a step pool and some of those parameters I talked about. You have hydraulic drop, you have velocity, you have water depth. It introduces the idea of energy dissipation factor. So in the pool, there's a certain amount of turbulence. So the turbulence, excuse me, the turbulence can confuse a fish. If it's too turbulent, the fish may get lost. But if it's within a certain range, it'll be able to find its way up and over. Yeah, there's another slide here. So these are hydraulic parameters, but it's unreasonable to expect that your stream or your structure is going to pass fish in all flows, because the fish really only move within certain flows. The California Department of Fish and Game has characterized envelopes for flows. So juveniles, it's flows going, this graphic here shows flow increasing as you go vertically. So on the left-hand side for juveniles, they have a lower and a more narrow range for juveniles. And there's a bunch of guidelines in CDFW. But conceptually, they have a high flow and a low flow. And within those two flows, you have a different set of hydraulic parameters. A juvenile can't jump more than a 1/2 foot. A juvenile needs at least 6 inches of water. A juvenile can't swim greater than 1 foot per second. So between those two flows, you have to design a structure or a habitat that will comply with those. Similarly, for adults, the bottom flow could be 3 CFS or it could be a different number. The high flow is 1% exceedance. And for an adult, between those two flows, you need to have at least 12 inches of depth. You need to have less than 1 foot of a drop, and the velocity needs to be less than 6 feet per second. But if you're in a 10-year event or say a 100-year event, you don't need to comply. I guess we could do this quickly, 34 minutes. Yeah, here's a quick chat question, Robert. If people can chime in, what are the issues on this concrete apron? What do you think are the passage issues here?
Any thoughts, anyone? Too shallow. Too shallow.
Indeed.
High temps.
Yeah. I'm waiting to hear the other one. I'll just keep moving here. Depth and velocity. You get super critical flow. It's shallow and fast. If a fish can only swim at 1 foot per second, it's out of luck. This is like a 50-foot ramp going at 10 feet per second. Yeah.
Velocity too high.
Yeah. And then sure, temperature, great egrets will go out there and have a field day and eat all the fish. They jump up on the apron. It's like a buffet. We're having a virtual buffet here. The fish will have their own buffet. Yeah, and the pool depths may be too shallow here. Okay, so real quick, fish barrier, a natural barrier. That actually looks like a barrier in Carmel, but I could be wrong. It could be a large wood jam. Other types of barriers, human-made. It could be a large dam. It could be a culvert that's perched, and say you had some down cutting and the culvert is now perched. You could also have what they call a partial barrier, which is temporal or physical. Like if you're in a tidal area, you may have varying levels that backwater or don't backwater. And yeah, basically limits life stage. So it's less of a barrier, but still a barrier and worthy of looking at. I realize that this is a group of Bay Area folks. So I just yesterday went on to the CDFW web viewer. It's called the California Fish Passage Assessment Database. So I just did a quick download. This is a pretty handy tool. If you go to this link right here, the purple, or rather the red squares, are what we call total barriers. And then the red triangles are natural barriers. So when it says total barrier, these red squares indicate a human-made barrier to fish passage. And then the unassessed, or the purple circles, the ones that are gray, are partial barriers. I don't see a whole lot of them, but they are in there. You can zoom in and out of the browser and look at it. These little stars on the right-hand side are related to unscreened diversions where fish might get trapped. So it's kind of a Bay Delta issue. But in terms of upstream migration, you can feel free to browse that and see how it affects your local agency. Design approaches. Okay. What do we do? How do we fix it? So there's a mechanical means. You could put in a Denis fish ladder for these little slots. You can put in a pool and weir fishway, with slots for low flow. recover a lot of grade, and then a vertical slot fishway. There's a lot of different ones. This is kind of interesting. They made, they made like a spiral version of a whirlpool fishway, kind of like a parking lot, parking garage. I'm not sure what the fish think about it. You can also do a natural restoration. You can do a rock weir fish passage, and I'm sure Valley Water has done a number of these. I'm new, I've only been here 2 years. You can also do a roughened channel. If you have a long reach, you can do a roughened channel with a lot of features without like a distinct drop. These are all in the California Department of Fish and Wildlife design guide. And I'll have that reference at the end. Or actually it's right here. Part 12 of the California Salmon Stream Habitat Restoration Design Manual. No matter how many times I present this and read it, I can never memorize that name. California Salmonid Stream Habitat Restoration Manual. So it's a really good reference. It's the go-to place when regulators say, "Hey, you gotta create habitat. You gotta sorry about that. I'm going to go back. I hit end accidentally, or not at the end of our presentation. Part 12. Yeah, this is the go-to manual for design, for restoration design in terms of in-stream habitat. It's authored by CDFW. So there's different approaches. There's stream simulation and there's hydraulic design. Stream simulation is where you simulate a reference reach. You simulate a type of stream you simulate a part of the stream that's known to provide passage. You don't have to do all the hydraulics. You just need to resemble the slope, the width, the shape. You basically go to a reference reach and you reproduce that on your site. Alternatively, you do hydraulic design where you show that we're compliant with depth, velocity, drop, etc. So you basically run all your hydraulic models to provide that answer. Make sure I captured that. Yeah, and you work with the swim-in abilities of the fish. Kind of revisiting that previous slide, when you design your structure, think about your profile. What's happening downstream? Is there a nick point that's going to migrate through my project site and blow it out? When I design my site, is there an existing plug of sediment or potential plugs of sediment? They're going to like plow through our site and totally bury my large woody debris habitat. Is it a riffle pool channel with a moving bed form? And the bottom of the bed form is going to come up to your site and move through. To think about your design profile in the context of the stream. Here's Singleton. Singleton's is a barrier that was actually recently fixed. I just thought I'd throw this photo in here. This is on Coyote Creek, near Singleton Road. It's basically this culvert that's perched. What happens is the culverts basically are blocked and you get this fast, shallow sheet flow, which is a total barrier to fish. Actually, it might be a partial barrier. They might be able to jump up into the culvert and swim through, but in higher flows, it's a total barrier due to velocity and depth. So Valley Water went in, they fixed it. Kevin Sibley at Valley Water is great contact. I think this is his design, but they put in basically a roughened channel and armored the banks, and again, thinking about bankfull width. They put in a free span bridge to be bigger than bankfull or at bankfull, just to allow the channel to naturally conform, naturally adjust. So I think that's a big success. It opens up miles and miles of a spawning habitat. Another example, San Clemente Dam removal. This is crazy. They moved the entire Carmel River. They dug a notch in a ridge, and they moved the entire Carmel River to bypass the sediment behind the dam. So here's a photo. It's a whole story, but it's kind of a cool photo showing the scale of the project. Instream enhancements. Okay. Great. So beyond fish ladders, beyond roughened channels, there's even more you can do to improve the habitat. I show a couple things here. What I indicate here are boulder erratics. So you could have a roughened channel, but if the roughened channel still is kind of funky and may not pass fish, or you don't have concentrated flows, or excuse me, if you really want to enhance it and you're concerned about passage, you could add some more diversity, put in a big boulder. And what the boulder does is it provides velocity or refugia. The fish will come up behind the boulder and they'll kind of hang out and rest, just so it can kind of recharge. And then once the fish is rested, then it can do sort of this little hopscotch thing between the boulders and work its way upstream. To help stabilize a roughened channel, you might want to put lines of large rocks on the edge, and then provide some sort of grade control. You could put cross weirs of large rocks to help stabilize your vertical profile. Otherwise, a roughened channel might just be like a bunch of rock dumped in a channel and shaped, but I think it's beneficial to provide some of these features. Beyond that, you can work with willows. You can work with willows and put willows between the rocks. I've done a lot of this where you do pole plantings between the boulders, and then the willows will grow up and through the rocks and stabilize your rock bank protection. It works really well. It could be a bit of a headache for stream maintenance because willows will grow, but it's really beneficial for the stream because it provides shade, it provides predator protection, avian predator protection, a lot of different things.
There's a question here about trying to facilitate juvenile and adult fish movement upstream.
Or in terms of enhancements, or
It just says, are you trying to do that? Are you trying to facilitate both juvenile and adults upstream?
it really depends on your project. If you have a large resident population of juveniles, you definitely have to do that. It usually gets dictated by the regulators. They tell you what you have to do. Or if you have a strong biological opinion of your staff, they say you should do this. But it really does get down to what the regulators tell you to do. They even confirm how high your drop should be. And beyond that, you really need to think about species. Like, I think lately we have Chinook salmon coming in, but historically it's steelhead. So on the coast, depending on where you are, you could be on the coast. You got like Central Coast steelhead or Southern steelhead. Species. Yeah, so you have to typically, perhaps you do both juvenile and adults, but yeah, think about your target species, think about your life stages, and then design for that. It's good to know ahead of time, definitely. So a pre-consultation is good to know. Like when you design your structures, you want to be able to comply.
Okay.
Now I'll keep going. There'll be time for questions at the end.
Yeah.
I guess to answer that question, juveniles love large woody debris. I've done a lot of large wood design. They can hide out here. You know, they can hide out from predators. They can feed. They can like hide behind the logs and pop out and feed. It's good for macroinvertebrates. It's good for gravel sorting. It's
Mhm.
good for shade, you know, temperature control. Yeah.
Okay.
Yeah, so I'm almost there. Guess I went faster than I thought. So
You're in good shape.
yeah, revisiting geomorphology. I have a couple bonus slides. I think I had like 50 something slides, but I was only supposed to have 35. Um, anyway, to kind of revisit kind of the key points, stream channels, they're not necessarily static, but they could trend to a dynamic equilibrium. You can quantify it by describing it as a bankfull channel according to bankfull parameters or watershed parameters. Definitely when you do a project, it's not all about your project site or reach. It's part of a system. Look upstream, look downstream, look at the history, you know. I think if you have, let's say you have a large dam and they're going to change the dam operation, not to name names, like Elwa Dam, you're going to want to know what the change in the flow regime is going to be. Or if you have historic meander belts in a system, you know, are you going to be able to restore it? Or if a dam does come out, you could potentially recover historic meander corridors for a stream. Anyway, thresholds. So I didn't talk about this so much, but a channel can build up a natural armor layer, and it's adapted to the dynamic equilibrium. If you get an episodic event, like say you get 100 or 500-year event, that armor layer in a stream can blow out and it can totally change your stream. And it can be a natural event, but there are thresholds in a stream where it's going to precipitate a metastatic equilibrium change. Consider a time scale. So, you know, the geologic time scale versus the modern time scale. You know, what is the design life of your project, and what's happening in the channel? What is the general geomorphic trending of your channel? Like if you see the sediment pulse from fire and you think it's going to take 5 years to go from headwaters to the bay, you know, think about what's going to happen. Or if you found a nick point down below and you can't fix it, how long is it going to take that nick point to reach your site, and what do you need to do about it? Fish or aquatic. Again, it helps to know for channel design the context geomorphically where a channel lies. It is, you don't want to design a dune ripple channel in a place where a cascade channel occurs. If you put in a pool riffle channel, does it make sense? You know, is it in the right slope range? Is it you know, is it in the right place? And the question asks, you know, what about juveniles and adults? You know your target species for when you design your channel, and what their requirements are hydraulically. You could tune in your hydrology. There's a lot of data analysis, but you can use the CDFW guide to guide your way to get your hydrology dialed in, because you can't really design until you have your hydrology and your hydraulics, and then you can know if your design fulfills your goals. As you can, create a self-maintaining bankfull structure, a bankfull channel with a structure and lots of hydraulic complexity, throwing rocks, throwing woody debris. Yeah, add willows. You know, I think Judy Naum at the district has some great structures on Uvis. You know, like she had, I need to go out and look at it, but she had like a mid bar woody debris structure, which was kind of interesting. And you could put root wads on the banks, and just, you know, we all need to kind of plan as humans for what we need to do, but think like a fish, you know, think about what they need, or a frog, or an egret, you know, think about the habitat that you're providing when you do your channel. So here's a list of references. This should be in the PowerPoint. Won't go through that necessarily. Some hyperlinks. And then I'm at questions now. 54 minutes. It's 2:58. Go ahead. Okay.
You're in good shape. Any questions or comments, anyone? You can just unmute yourself and speak if you like.
Guess I'll just throw in a comment. Great presentation, great information. Thanks for being here to present it.
Thank you.
It's a pleasure. Appreciate the bonus. Go ahead.
And just a reminder to please use the link in the chat to give us your feedback on this presentation. You'll also, by the way, receive an email after the presentation with the same survey link as a reminder to give us your feedback.
Great. Thank you. I decided to show this bonus slide. If you want to get fish passage, you could punch out a rock in a grade control for those who are interested. But okay. Yeah, thank you again for the opportunity to present. Appreciate it. Hopefully, yeah.
Yeah, Mark says this is my first introduction to stream bed details. Thank you very much for sharing this presentation.
Yeah, and I'm happy to answer questions if people want to email me. I can follow up. There's a lot of great information beyond this. I try to cut out some of the technical, and yeah. All right.
All right. Well, any final thoughts, Dennis, you want to give before we close?
Just you know, going back to context, you know, what does the stream want to be? What am I trying to do here? You know, how can I create a self-sustaining channel or stream or structure?
Does the stream want to be straight or curved?
Depends on the slope. Depends on that context. A cascade, you know, it could be straight and highly erosive, but maybe a dune ripple could be straight. So yeah, there's relationships between channel slope and sinuosity.
Thank you.
Braided, yeah.
Thank you, everybody. And just remember that we have 4 more presentations tomorrow. And I encourage everybody to register for those by going to the baywork.org website. I'll put that in the chat too. And look forward to seeing you at other Baywork events in the future.
Did someone have another comment? You were going to say something, or did you get it all out? All right. All right. Excuse me. Well, thank you, Dennis. Appreciate you being here and sharing this information. And everyone, please give us your thoughts. We like to hear about it. And you can use the link in the chat, or you'll receive an email as well regarding the survey. And join us again for some more great information. And we are interested in any topic that deals with our industry. And so we're trying to broaden our topics and so that we can touch more of our water professionals and share with the world the great work that we're doing. And so we've never done one on geomorphology as Baywork, and so this was a good introduction to it. And we, in fact, this sort of touched on a little bit in the presentation we had at 10 o'clock this morning regarding the watersheds in Sonoma from the fires. And so it has some components to geomorphology to it too as well. So thanks everyone. Have a great rest of your day. We hope to see you again, and be sure to stay in contact with us and stay abreast of what's happening with Baywork. Take care. Have a good day.